Hello, my name is Eric Stewart, and today I'll be talking about topology optimization studies in SolidWorks. So, essentially, topology studies are empowering engineers to do their core functions, design and optimization. And the way that works is a solver is going to take this solid mass. We're going to apply whatever loads we need for this body to hold. It's going to look at how the stresses move through that body and using iterative techniques, remove elements one by one in areas where stress is not to reduce the total mass of this body to meet the desired goals. So, given that 3D printing and additive manufacturing is more and more attractive and readily available, this is becoming a more useful tool every day. Now, this is not limited to additive manufacturing. You can also use subtractive manufacturing and machining to make parts with this, and also casting and injection molding as well. Now, what you need to do for this process is you're going to take your part and give it the maximum available dimensions for the simulation to work with, or the optimization. Here I have this bracket that I made with a little bit of weight savings by cutting this middle component out, and I've solidified it to the maximum dimensions because it needs to fit between these between plates that sit around the outside and have pins go through here. And we're going to run a static analysis on the part given what loads we can expect it to face, and then we're going to take that analysis and copy it and turn it into a topology study. So, what are the goals and constraints? Well, there are three main goals that we can set: mass minimization, stiffness to weight ratio optimization, or reducing the maximum displacement. And all of the constraints are pretty straightforward. You can reduce the amount of displacement if you have boundaries that you need to keep your component in. You can also have mass reduction goals. You're also able to say, hey, there are certain natural frequencies we need to avoid. Let's keep those below a certain value, and in different modes as well. And what we are looking at today is, in fact, the stress or factor of safety constraint, trying to keep that below 3. So, what are the manufacturing controls? Well, for our tool, we need to preserve the regions where it is pinned and connecting to other components. So on the shaft here, that's going to go into a bearing, and then these 3 holes are pin holes for where the pin connects this part to another. Now, you're also able to keep contact surfaces. If I needed this to support another piece, you could put a preserved region there. And for those preserved regions, you can specify thickness. So you're using certain materials, or if it's only practical to have beyond or above a specific thickness for a part to actually function or be manufacturable. And you're also able to use demolding direction. So if you're using injection molding or casting, you might need a draft angle. This is going to allow you to set the direction for that, or 2 directions if you're casting and have a 2-sided mold. Now, also looking back, our component is going on loading, and that is not symmetrical. We have loading in 2 different planes and not evenly spread out about this part. So we also need to use a specify symmetry plane constraint here, or control about that center axis. Once you have it fully set up, you can start solving, and this is what that looks like. You have your progress bar here. You can click on the view convergence graph, and that'll show you your goals, constraints, and the value of the most recent iteration. And if you click on these icons, it will also show you what the iterative process is putting out, and it'll essentially run a number of iterations until it has reached some level of convergence that meets your goals, and even gives you blue lines to show you what those goals are. Now, the output is going to be this amalgamation of elements where the ones that you need to keep are in yellow, and the ones that are okay to get rid of are different shades of blue based off their necessity. and the clear areas are just not touched by the stress at all, aren't okay to remove. Now, this is a pretty weird result here, considering that this pin cannot be freely floating. It needs to attach to the body. But what we're going to do is take the lessons learned from this, being that it's created outside plates and almost like a hollow center with these little land bridges to support the plates to each other. And we're going to essentially use that optimization feature and connect it to this bottom pin as well, and kind of use that design language in our part. But the way you can do that is you can either just take an STL and smooth it out, makes it printable. You can just throw it into your slicing software, or you can overlay this part onto yours, and then it's basically like a ghost. It's opaque, and trim away as needed. And that's what I chose to do. But I was having a little bit of difficulty with the geometry, and like I said, we are just going to use the design language. The hollow center, the little masses in between to support the outsides, and keeping those pin structures well supported as well. And what you see is our part got a over 85% mass reduction while still meeting our factor of safety goal of 3. Now, how manufacturable is this? It might be tough for machining, but it definitely looks moldable. And the way you design your part is definitely going to come down to what manufacturing constraints you have, but the results speak for themselves. Now, we did run this topology study on a separate part. It's actually the piece that connects to these pins, the arms that support a solar panel, and those loads that we saw in the previous study are here as well. And given the maximum boundary condition, you see it actually just cut the plate in half, and so that was good enough. I was hoping that it would take these square tubes and perhaps show me maybe just a solid plate that went out to the corners, but it didn't do any tricks that us engineers know. It wouldn't take advantage of any geometry or get creative at all. It will simply work backwards from where the stress is and again go element by element. So I think it's clear to see that this works best for solid bodies, because it's not going to understand how we can optimize using math. It is simply working backwards. So if we look at this little bracket here, in summary, we can see how this bracket is an ideal item. You know, it's solid, it's got a couple connection points, but the way that the stress moves through it is not complex, and we can refine it. And it looks like this bracket is already injection molded or printed, and it is still here, but now it is optimized. So yeah, best use cases are areas where you have a solid body that needs to be lightweight and optimized. You might think aerospace applications or cost saving, mass production, things like that, where you have the ability to do simple manufacturing changes that are going to save you a lot of money there, or optimizations. But we do have the limitations of the solver not using conventional geometry or those creative solutions. As far as processing goes, looking back at these studies, this for just cutting this plate in half took 41 minutes, whereas the design study I did, looking at different square tube dimensions, going from 1.5 to 0.75, 0.75, only took about 5 minutes. And its results were great as well. And this one, the solver actually didn't even give me a valid answer. Factor of safety of 32 and mass over doubled. So there are definitely limitations there. And I don't have the time on this, but I can tell you that it took about 21 minutes to run this study. And what we're actually going to do is take this and optimize it down, run another static study, see how the stresses move, and then probably change your variables again. So it's not as straightforward as running a single study. You're going to do it a couple times for the most optimal result. Thank you. I hope you learned a lot, and I hope you get a chance to use this tool in the future. Have a good one.